Thank you. It's coming. Okay, so I welcome you all for my presentation on I study on first degree cellular automata and application under the guidance of Dr. Kamalika ma'am. Here is my outline. I'm going to present my proposed work 1, 2, 3, and 4. 4 is under work in progress. So we'll be presenting on the first in study of first degree cellular automata for randomness. As we know, unlikely chaotic system, first degree cellular automata is a structured way of predicting and predicting the randomness, and along with the isomorphic classification, clustering as an application for first degree cellular automata. Let's discuss one by one. So as we all know, CA has a wide variety of representing the computational analysis, represent the computational complexity. The major challenge of the CA has been we can see that the representation. So our broad scope of the CA introduces the challenges in the mostly in representation, analysis, and computational efficiency. So because of that, we are introducing first degree cellular automata, which is also a subset of CA, and this is best suitable for our randomness, isomorphism, and clustering applications. Here is the definition of the first degree cellular automata, where we can see this equation as uh, demonstrate that the first degree cellular automata, if it is it can be represented as this, where this D represent as a state of the CA, and this CI denote the constant value, and these XYZ have the three neighbors for every for each cell, where XYZ is a subset of S. So mostly we are concentrating on over only three neighborhood in this work. We all knows that the butterfly effect was introduced by Edward Lorenz. So in that we can see that as a tiny change in the initial conditions will give the huge difference in the outcome, as well as in the repel in the ponds. We can see the lot of chaotic behavior, as well as in the chaotic behavior. So our motivation is to represent CA as a randomness. So how to represent our this first degree cellular automata in a simple form. So now we can represent through the RMT. Let's see that this is the three state FDCA rules, having these are the parameter value over this, these are the generated rules. So as we can see that all the randomness properties randomness properties dependent on the state in this work. So we are claiming that the randomness property will be dependent on the D. So using pen and paper. So for the simplified form, we need some extra rules. We need to categorize all the rules to check whether these rules are chaotic or not. So for that, we are using Z and P chaotic parameters. Along with this chaotic parameter, we are also checking and verifying with the space-time diagram. So let's see in the next slides. So why we are choosing the first degree cellular automata? Here are some PRNGs available over here using these empirical tests. These are the empirical tests, die hard, NIST test U01, in which we can see this LCG and LFSR PRNGs are there, in which we can see this SFMT giving the best result out of it. And now we can see in first degree cellular automata, it is mostly comparable with this PRNGs. These are this first degree cellular automata almost pass these tests. Uh, we can note that this work has been extended work for the first degree CA introduced by Kamalika ma'am. So our this scheme is work for any D state and M neighborhood of the CA. In this work we use, as I told, two chaotic parameters we have and based on this we are using this space time diagram for chaotic analysis. Actually for the big rules we need some greedy approach to reduce the rule spaces, so we are also looking for that. um, for the time constraint, I'm reducing some basic terminologies. So we are just quickly go through with. We are skipping some basic terminologies, so we will quickly go through. So for selection criteria of these rules, we will focus on the flow of information, balanceness like equal number of zeros and ones, non-linearity, large cycle, and it should be large like cycle length for the good PRNG. Chaotic property we are also using this in this work. So uh, let's see the jet parameters, which is introduced by Andrew Wench in 1998, and we are mostly considering p parameters because this is the best among this jet parameter and p parameters. So for our CA, we are considering this parameter as if we are having this L and R value will greater than 0.75 and R value is greater than 0.5. So then we can say that these parameters are best for our uh, PRNGs. These are some sample rules. So our selection strategy will also dependent on the D state as we are claiming. So like if a tiny change in the initial condition, it will give the huge difference in the output. So let's see using this space-time diagram. Some samples rules for this first degree cellular automata. We are showing the space-time diagram. This is a sample test. So we can see that in this diagram there is a no change for this rule, but for this rule we can see a lot of chaotic results has been coming. So we can say that this observation, we can say that this observation will strengthen our claim that increasing the number of D will also increase the randomness property. So these are some more sample rules, and we are considering mostly from D2 state to 10 state. We check over this, and we have given the sample of this experimental result. This is the details for 3 state, 4 state, 5 state also is there, and but I didn't include in the slide. Now come into the isomorphic classification of first degree cellular automata. So as we all knows that isomorphism means having two system having the similar structure similarities. So how we will check in the challenges in isomorphism in CA has been expensive and difficult because there is a dependent on the arbitrary this M like neighborhood, cell state, and all those all those constant and parameters has been considered. So it is very difficult to find out those isomorphic results. So for to verify our isomorphism and to study the isomorphism, we are taking a configuration transition diagram as a characterization tool. So if we can say cyclic is a configuration which form a cycle called as a cyclic configuration, otherwise it is called as a acyclic configuration. So for all the configuration of a CA or cycle, then it is a kind of reversible system. Otherwise, it is called as a irreversible system. For our study, we are only considering the reversible system. So here we are directly going to the synthesis of this scheme, where we can say that this hold the equivalence relation, which is reflexive, symmetric, and transitive. In this work, we are introducing two methods. First is map, and second is state exchange method. So we will see in the next slides. Let's take an example of three-state four-cell CA under null boundary condition. This is the FDCA. Sorry for this image. Actually, this looks very blur, I guess. It's okay. Okay, so we are fixing 0 here, and we are changing 1 and 2 with 2 and 1. So while changing this 1 as a 2 and 2 as a 1 and fixing the 0, so we'll get this same configuration transition diagram. So we can say that these are isomorphic. So let's take a very quick example. So this is the method for state exchange state exchange. Let's consider two configurations where these are the bijective mapping, as we knows that these are the property of the isomorphism. So we can say that these are isomorphic when those structures has been similar. So let's take an example quickly. We can see that in this state exchange method, when A, B, C, D, this C and D part has been changed with D and C. This configuration, let's see. Sorry. So there is a no change. We can see there is a no change. But here there is a no change. But here 0, 1 will be changed to 1, 0. Like that, we are changing all the configurations. So while changing all the configuration, we will get the isomorphic result. So this is the diagram for this state exchange method. Now we'll move to the second method, state map method. In this state map method, we are again considering two configurations. In this, we are just changing the bit, like second bit we are changing. We are just taking the complement of this B. So we can see this in this configuration, we are just changing here, we are changing. So again, we will get the same configuration transition diagram. So these two methods has been introduced in this isomorphic results, and also we will have the experimental result based on the cyclic structure of this FDCA. So we will analyze based on these parameters: number of cycles, average cycle length, maximal cycle length, and cyclic structure. Here we can see that these two parameters lies in this. Let's consider 4-cell length. We can see that these rules are isomorphic classes. 3 classes are there: 1, 2, 3, and non-isomorphic classes are 2 here. So we have completed till 10 state of this FDCA rules. So our next work is clustering with Gödel number and decimal first degree cellular automata. In this work, we are mostly we knows that the clustering is a key process of unsupervised learning. There is a challenge for the high dimensional data set. Mostly K-means and DBs can struggle to produce the meaningful cluster. So our motivation is to to have the less intra-cluster distance, we are introducing a Gödel number-based encoding techniques over the data set without losing the essential feature property, resulting is more effective clustering. That's why we are using Gödel encoding techniques. This encoding techniques generate the decimal string which are utilized in multi-stage clustering algorithm, employing in a reversal. Mostly we are using in the reversible CAs. So here some methodology we are using. I'm not going in depth of this because it's taking a lot of time. So it will take a lot of time. That's why we are just skipping some of the part of my paper. So we are using this P parameter again here in this work, and clustering metrics and benchmark like Silote score, CH score, and DB score. And our selection of the first degree cellular automata has been taken from all the n reversible rules 1080. Out of it, we are taking only 280 rules for our work. So all data sets has been taken from this this repository. So in our clustering method, we are using two merging method. First is median method, and second one is average method. So let's see, and also we are using the, as I said, Gödel number we are using into the to make the segment of the to make a string of the data set. So we are actually splitting those segments, string segments, into some couple of splits to reduce the complexity. So here is the flow diagram how we are implementing our work. So first we are first in this work, first we are generating the data frame through Gödel number, and second then we are applying on those data on those generated strings rule. Then we are using the iterative method to make the clusters. This is the flow diagram of our work. In this merging method we are using, let's see the average method. In this work we are just taking the average of let's suppose we have 4 clusters and we have to cluster this for 16 and 60. So we will first see the average of these clusters, then we will add this 16 to every clusters and make again a new average. So we'll see the minimum distance, minimum intra cluster distance. So again we will merge in this new cluster. So we'll finally in the final step we can get this final cluster. In the second method, median method, let's consider 3 initial cluster 2, 4, 6, 1, 3, 5, 7, 8, 9. In this we are taking this just median of it 4, 3, 8. So then again we will sort those medians. Then we will see what is the largest gap, d minus 1. What is the largest gap in between. So we can see that 4 to 8 is the largest gap. So we will make a 2 final cluster with 1, 2, 3, 4, 5, 6, and second cluster is 7, 8, 9. So this work has been already given in this GitHub repository. So our result find out that this over this data sets, over 6 data sets, iris, wholesale, seeds, heart failure, body move, and user knowledge, we'll see that these 2 results are like from this average matrix we are getting iris dataset having the good result, and this in median matrix we are having 0.79 as a good result in this. So these are our comparison with the existing clustering methods. So our fourth work is in progress. So we are just working on it, and we are just finding some theory. We are trying to theorize, and we are getting some beautiful behavior in the irreversible cellular first degree cellular automata as well. So these are some we just trying to finalize our work, fourth work. So here is the some conclusion and the future work of our first work. This is the in this first work we our model work for the NED and M neighborhood. We use the Z and P parameter chaotic analysis with the verification of the space-time diagram. Our future work is to go for the some higher dimensional cellular automata. So in second work, isomorphic classification, we find out that the all permutation of the states will go to d to the power n factorial. Here I think some mistake is there. So, and our future work would be we can find out the exact count of the partition in the given size. In clustering work, we study and demonstrated how Gödel number encoding helps us to enhance the clustering outcomes and reduce the complexity of our work. So we have done in the 3 stages of the FDC algorithm effectively identified. So our future work is for this work goes to refining the some more merging techniques we can check. So here list of publications, and I will also acknowledge some of my mentors, Professor Sukanta sir, Dr. Kamalika ma'am, Sukanya ma'am, and my co-researcher Baby ma'am. Here are some selected references for our work. Thank you for your valuable time. Question and suggestions are welcome.
Thank you, Vicky. Now it's time for questions.
So you have in the classification,
Not classification,
clustering. You have considered mostly reversible. You have said mostly reversible.
I mean, not mostly reversible only.
This is all the CAs you have considered is reversible. And what about the irreversible CA? They have some of. Suppose you have a irreversible CA and that have 3 or 4 connected components that forms this limit cycles. Suppose then have you tried these things? I mean, what the
no, only we have explored the reversible part of this. We have taken the reversible rules, and using those reversible rules, we are testing with these merging techniques.
Okay. No, my doubt is, I mean, what you instinct that there exists some irreversible CAs that have several connected components. Each component have a limit cycle. You consider finite, na? So
Yeah.
Limit cycle have each connected component. So you can cluster in that way. I mean, so in the previous day, I have seen one slide of Sukanya ma'am's presentation. She considered that things. I mean,
Okay.
I have doubt that. Have you explored that thing?
No.
Okay. Okay.
Vicky, I have another question. Suppose for the same data set, what you use user knowledge, previously we also used the same kind of data set. Now, are you getting any advantage over the number of levels by the method of clustering with what you have proposed?
Yeah, ma'am. So in terms of
Only one level.
yeah, ma'am, only one level.
Okay. Okay.
Hello.
Hi.
So a very basic question. Also, you have done a lot of extensive work, but one basic question, which I don't know. You have talked about how Gödel numbering scheme improves your clustering work, but what exactly is Gödel numbering scheme? If you could explain.
Okay. Just before sir introduced that, and Raja sir introduced that the Gödel number.
Yeah.
So in Gödel number, mostly there is a positive integers. Can I write? Okay, sir. There is actually a positive n integers of the sequence. Let's suppose one data set is there, hypothetical data set. Let's suppose 1, 2, 3. So for Gödel number, it's basically n prime numbers. Okay. N prime numbers to the power g1, and this prime number raised to the power the sequence of the values. So those are in the product form. So 2, 3, G2 into 5, G3 into 7, G4, like that. Yeah.
Vicky,
Yes, sir.
in your work, how many theorems you have developed? Theorems? I didn't see any theorem.
Theorem
the
in which part, sir?
Whole work. How many theorems are there?
That I didn't count, sir. But
You have theorems, no?
for isomorphic classification, we have developed two schemes: state exchange and state map. And
the schemes I have seen,
yeah.
but no theorems in your work.
Theorem is there, but I didn't include in presentation. One proof is there, sir.
Proof is there.
Yeah.
Achha, first question, a very basic question.
Yes, sir.
Why do you call the first degree CA? I can see the expression.
Yes,
it was some XYZ.
Yes, sir.
It should be degree 3. Why is first degree? Why are you calling it first degree?
Subrata, not working. Not working.
Yeah, the next. Yes.
Yeah, this one.
C0 XYZ.
Yes, sir.
So degree of X1, Y1, and Z.
So all degree is one only.
Sorry?
So in this equation, we can see the degree is one.
Degree
Is one.
of this polynomial you have written, na?
Yes, sir.
So degree is 3. You have taken XYZ.
Okay.
Are you saying like this?
Pardon, sir, I can't get you.
C in the polynomial C0 XYZ.
Yeah.
Degree of X is 1.
Yeah.
Y is 1 and Z is 1.
Z is one.
So if I consider this polynomial,
Yes.
then it degree becomes 3. So you have taken, as sir is saying,
Yeah.
so is it like this? That degree of each variable X, Y, Z, they're 1. So you are calling it first degree. It's like this.
Yes, sir.
Okay. Well, next point is, okay. But this kind of question may come. Why are you calling it first degree? But it shouldn't be first degree. Second point is you have taken two parameters, Z and P. I didn't find why two parameters. There are other parameters. So lambda parameter was there.
Lambda parameter.
Why lambda is excluded? And if you want to exclude, you can work with one parameter only. So Z might may be useful, or maybe P parameter will work for you. Why two parameters you have taken?
Sir, basically, these are the best parameters out of this lambda parameters and.
Well, if P is the best, suppose P is the best parameter, then P will work. You are choosing some rules, not based on the P, some parameter, right?
Yeah.
So why two? Why Z and P?
Yeah, we can check with other also.
No, is the question clear? You have
Yes,
taken
sir.
two parameters, na?
Yes.
So why two parameters? I didn't get this logic. So suppose you are taking one parameter. Maybe that is good or bad. So based on that, you can choose some rules as
Yes,
chaotic, which you will use for your purpose.
Yes, sir.
So why two parameters? Any conflict is there that Z parameter is saying no, this is not good, but P parameter is saying this is good. There should be some conflict.
Yes, sir.
Okay, then what you are doing?
So mostly in P parameters, we are using the information cooking and information propagation. So in this work, we can get most P values, like most P values in left information propagation. And right.
That is all right. Go to that slide. Maybe you have taken the rule. Yes. In the methodology, just you have taken two chaotic parameters, that Z and P.
Yes.
How are you using this Z and P? Right. This is not clear to me.
Okay.
One reason may be, I don't know whether you have used it, the OST proposes Z parameter, that is for the binary CA.
Binary.
Since you are taking NED, then you are using P. Is it like this?
For
No.
for chaotic parameter, yeah, we can do for NED for this P parameter for any like any NED
Okay.
we can use.
Well, you find this answer. I don't know why two parameters you have
Yeah.
taken.
Yeah.
And regarding isomorphism,
Yes.
do you have proof? Is it NP complete problem?
Yes, sir. NP complete.
Be-
NP hard. Sorry. I see you.
So two C are given.
Yeah.
So go to that slide. There is no statement like Suppose two CA,
Yes, sir.
even two first degree CA are given. You want suppose the problem is to decide whether two CA are isomorphic or not. So is it? Can you write the program? Is it doable? I mean, in polynomial time.
We tested till D10.
Okay, you don't. Then
So
the question is you have synthesized the
synthesize. Yeah. We go through the synthesis scheme.
Okay, yeah. So you have maybe two schemes you have represented. Two
State,
schemes.
yeah.
Is it exhaustive? I mean, is there other scheme? I mean, the other CAs are there, which will be isomorphic to some CA, or this is the exhaustively you can find the isomorphic CAs.
So for that, sir, I can show some results.
Oh, that is all right.
Some results like it goes exponentially and it is like very exhaustive. So I can show the results.
Oh, then apart from state change,
State exchange and state map, sir. This is state map, sir. We are taking the mostly complement.
so these two approaches you have taken.
Yes, sir.
So is it possible to have other approach
Yes,
to
sir.
get
Maybe
other?
we can find the exact count of the isomorphic CA because in this there is a dependency of the neighborhood, the state map. So
Okay, have you not?
no, sir. Yeah, there is some problem with the neighborhood dependency. So I can show in the last.
And final.
Just wait, just a second, sir. So I taken the lot of animation. That's why it's getting. Yes, sir. I took in appendix section actually. So this looks very. These are the results on this experiment done on the ECS. So we can see that this.
What is this? This is the next first one is the given CA1.
Sorry.
And the next the previous are the next. I mean the
State
next
map and
CAs
exchange. Yeah.
they are the isomorphic CAs, right?
Yes.
Okay.
We are taking the some
that you have
uniform
designed.
CAs.
My question was whether it's possible to get other CAs which are isomorphic, which you have not covered here. You should, get for some cases at least.
Yes, sir.
Right.
Definitely will discuss.
So you should put this kind of comments also
Yes.
while you write the final thesis work. Yeah. And my last question, although the question was asked, any advantage of Gaussian number? Why are you using Gaussian number? It's not very usual.
So when compared with the hashing technique and frequency encoding techniques,
Any idea why it is so? Why Gaussian number? Gaussian number is very interesting.
Yes, sir. And prime numbers we are taking, and then we are generating.
Why have you used clustering? There are several techniques. Gaussian numbers are not used before, right? So why it is so? Any reason? I mean, any point you have, or just arbitrarily you have tried and then you observe that it is giving good result.
So I can't say much right now.
Okay, this should be written in your.
Yes, sir.
Thank you.
Thank you, sir.
Okay, Vicky, you have a lot of work to do. So, okay. So now we'll
Thank you.
Thank
you, sir.
Ask the next presenter. I think Amit.
Yes. Thank you.
So I believe that is the benefit of having a PhD forum where you can actually get to know where you are lacking.
How's it? Within 20 minutes? 30 minutes, no? Done?
PhD হয়নি কারো? ও এই হয়ে গেছে? আচ্ছা।
Okay, good afternoon, everyone. Myself Amit Kumar Pramanik. The topic of my PhD is synthesis of efficient and reliable QC logic circuit under regular clocking scheme. I'm not going into the details of this QC because yesterday I have already discussed about the basic. So I'm going into the directly into my contribution part. Uh, that is. Again, before going to the contribution, first I want to tell some motivation behind my contribution, and mainly four motivations are there. First one, according to the previous research we have identified that many research has been done targeting towards the minimization of majority voter, respect of the inverter. But we know that in QCA, majority voter and inverter are equally very important in the realization of any QCA circuit. But many focus has been given only to the majority voter rather than inverter. So that's why my first contribution is that investigation of a proper mechanism of cost efficient circuit synthesis targeting towards inverter reduction. The second one is that in digital circuit many circuits are there which is very much important, like just like multiplexer, adder, latch, flip flop. But in case of research in QCA, many circuits realized in for this sorry, many structure are realized for these circuits, but none of them investigated which are suitable clocking scheme for these uh, digital circuits. But we know that clocking plays a very much important role in realization of any QC circuit, but this one is missing. So that's why the second point is that analysis of reliable regular clocking based fundamental circuit. And the third one is that regarding the genetic algorithm, again from the previous research we have identified that elitism based genetic algorithm is very much important, or it has very much impact in optimization of QCS circuit. But none of the previous research investigated the elitism based genetic algorithm, and at the same time they have not considered all the basic parameter can be used and which are impactful in case of calculation of cost. So that's why we have investigated an elitism based genetic algorithm for cost efficient QC circuit synthesis. And the last one is that whenever we have developed something, we need to scrutinize or investigate the performance of that one. So that's why we have developed the genetic algorithm. In the last part, we have investigated the performance or the impact of the genetic algorithm in respect of cost, fault tolerance capability, and the power. So that's why this is my flow of the thesis or the defense. The first contributed one. In that first contributed one, I have identified four rules, basic rules. First one is the De Morgan's rule. Second one is the Zorbest rule. Third one is the majority to minority conversion, and the fourth one is the well-known function. By that, we can minimize the number of inverter for any Boolean function or Boolean circuit. So this is the basic algorithm is given for the reduction of the inverter. But in one thing, another thing is that every time inverter reduction is not possible. But in that case, if we place the inverter in such a way that we can minimize the cost of the circuit. So that's why in case of second algorithm, that one is the placement of the inverter. These are the basic two algorithm I have used for the placement of the inverter and the reduction of the inverter. Regarding this paper is published, and we have investigated the performance of these two methods, means the placement and the reduction, by using different function. First one is a 13 standard function we have used to evaluate the performance of this method, and we have find out that in case of our method takes only 17 inverter, previous method considered 24 inverters, and the conventional method 30 inverters. So we can find out that our method significantly reduces the number of inverter. And that way we have also checked for the other two input symmetric function, three input symmetric function, and many other different type of adders we have also checked, and some benchmark function we have also checked for this regarding or for this concern. And in every cases we have find out that our method optimizes the number of inverter in realization of any Boolean function. So these are the first contribution. And the second one, and the second one, as I have discussed, that we have taken four different digital circuit, flip-flop, latch, multiplexer, and the adder. In this respect, we have tried to find out which clocking scheme is suitable to realize these four different type of digital circuit. So in this respect, we have taken four well-known clocking: USC, RES, optimized studio, and zigzag. First, we have tried to find out the HDLQ to find out the fault tolerance capability, because we have find out the suitable clocking scheme in terms of fault tolerance capability. So first, this one is the HDLQ model for 1-bit full adder. Just we have first we have realized the all the all the full adder using the 4 different clocking scheme, and then after that we have converted this one into HDLQ model. In HDLQ model, mainly in this model we have represented the majority voter, inverter. Here L represents actually the L shape, M represents the majority voter. In that way we have represented the model. And in the same way we have represented for the 2:1 multiplexer by using different 4 clocking scheme. And next we have also used four different clocking scheme for SR latch and flip-flop. Next, in the next slide, we have tabulated the result. From that result, we can easily find out that for full adder, in terms of fault tolerant capability, optimized 2D performance is very much less in compared to the zigzag, and the performance of the zigzag is best compared to the other ones. But in case of mux, the performance of the zigzag is not so good compared to the other one. And we can combine in 3 cases. We can say that the performance is zigzag very much important or very much good for all the circuits, irrespective of the mux. But in case of optimized 2D, the performance of the optimized 2D is not so good for all the clocking, for all the digital circuit. So from this slide or from this case, we can say that the zigzag clocking scheme can be used for realization of realization of full adder, SR latch, and D flip-flop. In this regard, one paper was published in 2025. Next, the third one, the genetic part algorithm. This process started from the creation of the initial population, and after that the fitness function is used to calculate the fitness value. Depending on the fitness value, the elite chromosome is identified and it is carried forward to the next generation without any alteration. After that, modified 1 point crossover is performed, and after that a mutation has been done, and this process is continuous until it reaches to the desired result or maximum generation. In this respect, first, by this tree we have represented the each chromosome, and in this respect, suppose this tree is represented in such a way that, suppose if I take any integer number for majority voter, then we need to take 3 another number, because majority voter has a 3 input. In that way, the tree has tabulated or generated. After that, the pre-order traversal used to represent the number representations for this corresponding Boolean function. Then fitness 1 and fitness 2. In this regard, I want to tell that, and I have missed one thing. This mainly the genetic algorithm is targeted towards the optimization of multi-objective function. So that's why we have taken 2 fitness function, because from the previous research we have identified that if I take the single fitness function for multi-objective function, it may not possible to optimize all the output. So that's why the fitness function 1 is calculated for the initial output, and for the other outputs, the second fitness function is utilized. And in that case, in the second fitness function, we have calculated we have find out the common majority voters and for common inverters. And another thing you can find out that in case of total gates, we have given the priority total inverter by 3, because as majority voter has a 3 input, but the inverter has a 1 input. That's why we have prioritized the inverter less compared to the total majority voter, and that way the fitness 2 is calculated. After that, the total overall algorithm is given over here, and for this contribution, I have published 2 papers which is represented here. Next, again the comparison has been done. In this respect, I have tabulated, I have taken 5 different output function. Here I have given only one result for 3 input and 3 output function. On that function, you can easily find out that our method in case of total gate optimizes 16.67%. In case of total gate, and for maximum level, our method optimizes 33% compared to the previous methods. In that many other functions are also compared, but I have not given here due to the limitation of the slide. And next, the work done 4. In this part, I have scrutinized or investigated the performance of the before mentioned genetic algorithm in respect of 3 parameter: cost, fault tolerance capability, and power. In this respect, I have taken 4 different output function, which is taken from the 5 different group. Next, again, in this slide I have represented the cost 1 and cost 2. Again, by using 2 cost function, we know that in QCA 2 cost function are there. By the cost 1 is actually combination of area and delay. Cost 2 is the cost 2 uses majority voter, inverter, wire crossing, and the delay. From this tabulation or from this result, we can say that, or we can find out that for P1 function, after applying genetic algorithm, the number of gate almost not exactly same, but the circuit area is increases, because we know that in sometimes after using regular clockings, circuit area may increases. So that's why these things happen here. As a result, after applying genetic algorithm for P1 function, the cost is also increases, because cost 1 and cost 2 depends on the area. But in case of P2 and P3, we can easily find out that cost decreases, cost 2 decreases, because the number of gate and the area also decreases. Again for P1, but in case of P1, thing is that the number of gate is increases after applying genetic algorithm. And as a result, the cost also increases. But in case of P5, the number of gate decreases, but as the circuit area increases, it increases the cost too. So this is the effect of or the impact of the genetic algorithm in respect of cost. Next up, power dissipation. From this power dissipation, we can say that for P2 and P3 function, the power dissipation is less, as the power dissipation of any QC circuit depends on the majority voter, inverter, and area. And after applying genetic algorithm for P2 function and P3 function, the number of gate and the circuit area also decreases. So that's why it has a very impactful effect in case of P2 and P3. But in case of P4, as the circuit area increases, at the same time the number of gate increases, it increases the power dissipation. And the last one, using the fault tolerance capability, again we can find out that from this tabulation that after as the fault tolerance capability only depends on the area, because we know that whenever the circuit area decreases, the fault tolerance capabilities also decreases, because in case of QCS circuit, when the circuit area is very much less, all the cells are very much important to provide the correct output. Whenever we will remove any one of the cell to check the fault tolerance capability of the circuit, in that case it provides the wrong output. So that's why that's why in case of P3, as the circuit area decreases, we can easily find out that P3, the fault tolerance capability before applying genetic is 65, after applying it is 36, because after applying genetic algorithm, as the circuit area decreases and the number of bit decreases, is also the fault tolerance capability decreases. So this is we can say that the P4 function actually has the genetic algorithm is a reverse effect. So now I can conclude that in my research I have find out four different things, mainly two different things. First one is I have reduced the inverter in realization of any Boolean function to realize the circuit. And next, in the second, I have find out the suitable clocking scheme to realize the well-known digital logic circuits. And the third one, I have find out one genetic algorithm based on the elitism, which can optimize the multi-objective function. So these are the references I have used. Thank you.
Okay, thank you, Amit. Now questions.
Can you say something about the physical parameters of the dots? For instance, how large are the dots and the distances between the dots, and where the wires, the clock lines are placed? I think they are placed between the dots. I think so.
Sir, actually, in case of dots, there is as is a proton. As is an electron, there is very much less space. At that time I cannot remember the space, actually the unit or the value, but it is very much less, as it is an electron. And in the electron, 4 quantum dots are there. Inside these 4 quantum dots, 2 electrons are present. I'm telling wrong way. In QCS cell, 4 holes are there. Inside these 4 holes, 2 electrons are present diagonally opposite. As if the electrons are placed diagonally opposite position, then the Coulombic reaction is very much less. And the unit or the value I cannot remember at that time, sir.
Okay, my question was also how many nanometers or
nanometer. It may be nanometer, but I cannot remember, because
something like
very
that.
much QCS is very much small.
In the atomic level.
Very much.
Okay, thank you.
Yes, sir. Yes, sir. Yes, yes.
I think the answer, sorry, one question is, or part of one question is, what nanometer technology you have considered. Depending on that, now, if you change the nanometer technology, the feature will also will change.
Sir, it is not clear to me the question. I want to say that we have used the basic QCA designer and so do the basic default parameter we have used.
No, no. So anything default, I think something
Yes, it
behind
has
that.
some value. It has
Anyway,
some value.
so if you go through your papers, there it is written.
Yes, it has some value. At that moment, I cannot remember that thing.
There are so many multi-objective optimization techniques.
Yes.
So why should you choose GA?
Because many other are also there, but according to the research, we have find out that GA has an impact in QCA. First thing. Second thing, from the also research, we have find out that elitism-based GA also has a greater impact.
I mean, have you compared with other techniques?
No. Because in previous
which kind of GA you have actually used?
Which kind of GA is
means NSGA2 or what is the exact GA you have used? There?
Actually, we have GA is there. We have modified the GA according to your convention.
Normal, I mean, plain GA crossover operator.
Plain GA is there in the basic case, the default case, but we have changes according to your requirement. Just like I have said that I have used two fitness function. In the normal GA, there is only one fitness function.
Yes.
But we had to minimize the multi-objective function. That's why we have taken two fitness function. And again, another thing is there, single one-point crossover is there, but we have used modified one-point crossover. If you can find out in my paper, because due to the non-linearity nature of the QCA. Means non-linearity nature means in case of majority voter, if I interchange the majority voter with inverter, then the output of the Boolean logic will be different. As the output of the majority inverter or output of the majority voter are different.
But most of the cases in multi-objective optimization in NSGA2 perform better than normal GA. So I mean, why do you not consider this thing? Because that one is the newest one, and that one is the best of the GAs.
Again, same thing. Suppose it may possible in some other field, but in case of QCA, we have find out only the basic normal GA is there. According to the research.
No. I mean, I just ask you, why do you not consider this thing?
The same reason.
Because previously some other person you are only following that path.
No, not like that way. We have tried the NSGA also, but that in that case it is not given that way. The solution is not so good.
Okay. I just like to ask you this thing that do you have this comparison or?
We have done that. We have find out. We have changed it.
Because I think if you show this type of comparison, that would be clear to the audience.
Okay, because there is a limitation of the
okay,
slide.
Fine. Okay, thank you.
You represented my 130 slides in using the only 20 slides.
Okay. Thank you.
Thanks.
Yeah, Amit, I have
Yes,
a
ma'am.
query. Like you are saying, in literature it was one single optimization function. You used two. What motivated you for two? Why not 3 or 4 or something?
In the future research, you can actually, ma'am, in case of this algorithm, there is a multi-objective, not only restricted to 2 outputs. We have used 4 output function. We have used 3 output function. We have also taken 5 output function. For all the parameters, different types of output function, I have taken to investigate the performance of the G. In this case, I have already represented the 3 output functions in my slide, but in this paper on the main slide, I have used the 4 output function, 3 input, 4 output, 5 inputs, 4 output, and I have different categories of output functions.
You mentioned about minimizing the inverters.
Yes.
So your technique gives the absolute minimum number of inverters, or it just improves upon the existing one?
This one is improved compared to the previous. We cannot say it will the minimum case, but it is the better result we are providing compared to the previous all the literature which are provided.
But I think there is work which can actually guarantee the minimum number of inverters.
We have not tested that one, sir. We have already focused. We have already identified that our result is much better than the previous one. All this depending, I have discussed we have taken different type of function, benchmark function, symmetric function, different type of adder, different type of symmetric function. We have taken different type of function to check this one. And in all the cases, we have find out that our investigation is very much good compared to the previous. Compared to the conventional one is also very good, and compared to the previous one also good, very good.
It's possible that it can be lowered further.
May possible, sir. By twisting the algorithm, by twisting the changing the algorithm, may possible. There is chances.
Okay, so I think there is work which actually gives you the minimum number of inverters.
Actually, sir, it is not that way. You can tell that you can have, we have an algorithm and that algorithm give the exactly the minimum value. Still now, not this type of is possible. Everyone is every algorithm is trying to provide some minimum result compared to the previous one, and nothing is there which is providing the exactly the minimum value. According to me, sir.
It's there. I can point you to that.
Okay.
Yeah.
Okay, any more questions? Okay, otherwise we can just thank him, and there are a lot of scope still to do, as always in research.
It's
And
research, it may possible every time.
yeah, and so probably you will take that feedback and work on it. Okay, thank you.